Hello friends, this is Jayant Ronkar working as Assistant Professor, Department of Information Technology, Tulsi Ramji Gaikwad Patil College of Engineering and Technology. Friends, today we are going to learn about server in client-server model of distributed system. As we know that server is played very important role in any client-server model. So in this section we will take a closer look at the organization of servers. In the following some topics we will see the number of general design issues for servers to be followed by the discussion of server cluster. So we will start with the general design issues of the server. A server is a process of implementing a specific service on behalf of collection of clients. In essence, each server is organized in the same way. It waits for an incoming request from a client and subsequently ensure that the request is taken care of, after which it waits for the next incoming request. Then there are several ways to organize servers. In the case of iterative server, the server itself handles the request and if necessary return a response requesting client. A concurrent server does not handle the request itself but passes it to the separate thread and another processes, after which it immediately waits for the next incoming request. A multi-threaded server is an example of the concurrent server. An alternative implementation of the concurrent server is to fork a new process for each new incoming request. This approach is followed by many Unix systems. The thread or process that handle the request is responsible for returning responses to file requesting client. Another issue is where the client contact to a server. In all cases, client send request to an endpoint, also called a port, at the machine where the server is running. Each server listen to a specific endpoint. How do client know the endpoints of service? One approach to globally assign endpoints for well-known services. For example, servers that handle internet FTP request always listen to TCP port 21. Likewise, an HTTP server for the World Wide Web will also or always listen to TCP port 80, that is 80. These endpoints have been assigned by the Internet Assigned Number Authorities, that is INA, and are documented in Reynolds and Foster, which is represented and given by Reynolds and Foster in 1994. With assigned endpoints, the client only needs to find the network address of the machine where the server is running. As this is required to find out the address, so there are many services that do not require pre-assigned endpoints. For example, a time of a day server may use an endpoint that is dynamically assigned it by 9Y, its local operating system. In that case, the client will first have to look up the endpoint. One solution is to have the special daemon running on each machine that runs servers. The daemon keep the track of current endpoint at each service implemented by co-located server. The daemon itself listen to well-known endpoints. A client will first contact to daemon, request the endpoint, and daemon the specific server, which is given in this figure, where the client will first request to the server, and according to that client will get the reply from the server. So this is what about the client to server binding using the daemon. In common to associate an endpoint with a specific services. However, actually implementing each service by means of the separate server may be waste of the resources. For example, in typical Unix system, it is common to have lots of servers running simultaneously, with most of them passively waiting until the client request come in. Instead of having to keep the track of so many passive processes, it is often more efficient to have a single super server listening to each endpoint associated with a specific services, which is given in figure B, where client to server binding using a super server. This is the approach taken, for example, with the innate daemon in Unix. Intent listen to the number of well-known port of internet services. When a request come in, the daemon forks a process to take further care of the request. This process will exist after it finish. So this is about client to server binding using a super server. Then we will see about the server cluster. In this we can see that there are client at the first tier requesting to the server, and then server will taking the data from the databases or database file the distributed system, and accordingly the server will process to the request of the client. So here in a server cluster is nothing else but a collection of machines connected through a network, where each machine run one or more servers. The server cluster that we consider here are one in which machines are connected through a local area network, often offering high bandwidth and low latency. In most cases, the server cluster is logically organized into 3 tiers, as shown in this figure displayed on the screen. The first tier consists of a logical switch through which the requests are routed. Such a switch can vary widely. For example, transport layer switches accept incoming TCP connection request and pass request to one of the servers in the cluster, as given here. A completely different example is web server that accept incoming HTTP request, but that are partly passes request to application server for further processing. Only the later collect result and return an HTTP response. As in any multi-threaded client server architecture, many server cluster also contain server dedicated to application processing. In cluster computing, these are typically server naming on high performance hardware dedicated to delivering compute power. However, in the case of enterprise server cluster, in many of the cases, that applications need only run on relatively low end machines, as the required computer power is not the bottleneck but access to the storage. This bridge is third tier, which consists of the data processing server, notably file and database server. Again, depending on the usage of the server cluster, these servers may be running on specialized machines configured for high-speed disk access and having large server-side data caches. So this is about the server cluster. In that it is divided into 3 tiers, and accordingly the work is to be done. Now we will see the principle of TCP handoff. A standard way of accessing server cluster is to set up the TCP connection, or which application level requests are then sent to the part of session. A session ends by tearing down the connection. In the case of transport layer switches, The switches accept the incoming TCP connection request and hand off such connections to one of the server. The principle working on what is commonly known as TCP handoff, as shown in this figure. It is called a TCP handoff. When the switch is received a TCP connection request, it subsequently identifies the best server for handling the request and forward the request packet to that server. The server is in turn will send an acknowledgement back to the requesting client, but inserting the switch IP addresses as the source field of the header of the IP packet carrying by the TCP segment. Note that this spoofing is necessary for the client to continue executing the TCP protocol. It is expecting to answer back from the switch, not from the arbitrary server it has never heard before. Clearly, the TCP handoff implementation require operating system level modifications. So, in any case, it already be seen that the switches can play the important role in distributing the load among the several various servers by deciding where to forward the request to and to which switch it decide to which server to handle for the processing of the request. So this simple load balancing policy that the switch can follow is round robin. Each time it pick up the next server from its list and forward the request to. So this is about the server cluster where the TCP handoff is to be done, and then we will see distributed server. A server cluster discussed so far generally rather statistically configured. In this cluster there is often a separate administration machine that keeps the track of available servers and passes this information to other machines as appropriate, such the switches. As we mentioned, most server clusters offer a single access point. Where that point fails, the cluster becomes unavailable. To eliminate this potential problem, several access points can be provided, of which the address are made partially available. For example, the domain name systems, that is DNS, can return the several addresses all belonging to the same host name. This approach still eliminates clients to make the several attempt if one of the address fails. Moreover, this does not solve the problem of requiring static access point. Having stability like long living access point is desirable feature from the clients and server respective. On the other hand, it is also desirable to have the high degree of flexibility in configuration of a server cluster, including switches. This observation has led to a design of a distributed server, which effectively is nothing but possibly dynamically changing the set of machines, with also possibly varying the access points, but which nevertheless appear to outside world as the single powerful machine. This design, such as the distributed server, is given by Sanzamic in 2005. We will see it next. The basic idea behind the distributed server is that the client benefits from the robust, high performance stable server. These properties can be provided by the high performance mainframes, of which some have to be acclaimed near time between failure of the more than 40 years. However, by grouping simple machines transparently into cluster and not relying on availability of a single machine, it may be possible to achieve a better degree of stability than each component individually. For example, such a cluster would be dynamically configured from end user machines, as in the case of collaborative distributed system. So this is about the distributed server. Now we will see about this diagram how the route optimization in the distributed system is to be done. In simple configuration would be make the home agent as well as the access point a potential bottleneck, as all traffic would be flow through these two machines. This situation can be avoided by using the MIP version 6 protocol features known as route optimization. Route optimization work as follows, where the mobile node with home address, that is HA, report to its current care of address, that is CA. The home agent forwarded CA to a client. The latter will then locally store the pair, that is HA, CAY. From that moment on, communication will be directly forwarded to CA, although the application that client side can still use the home address and underlying support software for MIP version 6 will be translate the address to CA and use instead of that HA. Route optimization can be used to make the different client believe that they communicating with a single server, where in fact the client communication with the different member node of the distributed server, as shown in this figure, where the route optimization is to be done in the distributed server. So to this end, when an access point of the distributed server forward a request to clients, that is C1, then it says to node S1, then it with address CA, that is CA1, it passes through information to S1 to let it initiate the route optimization procedure. By eventually the client is made to believe that the care of address, that is CA of R, this will allow C1 to store the pair, that is HA1 and CA1. During this procedure, the access point that is prepared, that is well-known home agent, tunnel most of the traffic between C1 and S1. It will be tunneled down the traffic between the C1 and S1. This will prevent the home agent from believing that the care of address has changed, so that it will continue to communicate with the access point. So this is about the distributed server. Now we will see the managing of the cluster, managing of the server cluster. In this we will see a server cluster, how it manage and how the working will be done. A server cluster should appear to outside world as a single computer, as indeed often the case. However, it come to managing a cluster, the situation changes dramatically. Several attempts have been made to ease the management of the server cluster, as given here in this diagram. The common approach in the managing of the server cluster is, most common approach for managing the server cluster is to extend the traditional managing functions of a single computer to that of the cluster. In its most primitive form, this means that an administration can be logged into node from a remote client and execute local managing commands to monitor, install and change the components. Somehow more advanced is to hide the fact that you need to log into node and instead provide an interface at an administration machine that allow the collection or collect information from one or more servers, upgrade components add and remove nodes. The main advantage of latter approach is that collective operation which operate on a group of servers can be more easily provided. This type of managing server clusters is widely applied in practice, exemplified by management software such as cluster system management from IBM. So this is what about the management of the cluster server. Here, as it turn out, support for every large server cluster is most always be ad hoc. There are various rules of thumb that should be considered, which is given by the Brewer in 2001, but there is no systematic approach to dealing with the massive system management. Cluster management is still very much in its infancy, although it can be expected that the self-managing solution, as discussed in various topics. So we will now see the topic, that is example of managing server cluster, that is Planet Lab. So we will now take closer look to somewhat unusual cluster server, that is Planet Lab is collaborative distributed system in which different organization each donated one or more computers, adding up to total number of hundreds of nodes. Together these computers form L-tier server cluster, where access, processing, storage can all be take place on each node individually. The management of the Planet Lab is necessary most entirely distributed. Before we see toward the Planet Lab, we will see the example of this Planet Lab. Here the basic organization Planet Lab is given. In Planet Lab, an organization donate one or more nodes, where each node is easiest thought of just single computer, although it would also be itself cluster of machines. Each node is organized as shown in figure. Each node is organized as according to the defined in the figure, where there are two important components. First one is virtual machine monitor, that is VMM, which is an enhanced Linux operating system, and enhancement mainly comprises adjustment of supporting second component, namely vServers. Here vServers are also given in this diagram. So a Linux vServers can also be bought, also be thought of as a separate environment in which a group of processes run. Processes from different vServers are completely independent. They cannot directly share any resources such as files, main memory and network connections, as is normally the case of processes running on the top of the operating system. Instead, vServer provide an environment consisting of its own collection of software packages, programs and network facilities. For example, vServers may provide an environment in which a process will notice servers, say HTTPD 1.3.1. In contrast, another vServers may support the latest version of the Python and HTTPD. In this case, in the sense, calling a vServer a server is a bit of misnomer, as it really only a isolated group of processes from each other. We return to vServers briefly. Linux VMM ensure that the vServer are separated processes in different vServers are executed concurrently and independently, each making use of only the software packages and programs available in their own environment. The isolation between the processes in different vServers is strict. For example, two processes in different vServers may have the same user IL, but this does not imply that they stem from the same user. This operation considerably eases supporting users from the different organizations that want to use the Planet Lab, for example, test bed, to experiment with completely different distributed system and applications. So this is what about the organization and architecture of the Planet Lab. There are several issues that make management of the Planet Lab a special problem. There are three silent feature problems that are listed here. One, node belong to different organization. Each organization should be allowed to specify who is allowed to run the application on their nodes and restrict resource uses appropriately. Second one is there are various monitoring tools available, but they are all assume a very specific combination of hardware and software. Moreover, they are also tailored to be used within a single organization. Third one is programs from the different slices but running on the same node should not interface with each other. This problem is similar to the process independence in operating system. Then this is what about the issues while designing or while discussing the Planet Lab. So then we will see the management of relationship between various Planet Lab entities. So in this diagram we can see that there are node owner, management authority, slice authority and service provider is shown, and there are link between link among themselves to show their relationship. So here the organization tends to the management structure which is given in this diagram, described in terms of the trust relationship, which is defined by the Peterson in 2005. The relationship is given as follows: a node owner put its own node under the regime of the management authority, possibly restricting uses where appropriate. A management authority, second one is a management authority provides the necessary software to add a node to a Planet Lab. Third one is a service provider register itself with a management authority, trusting it to provide well behavior node. Fourth one is service provider contact to a slice authority to create a slice on the collection of nodes. Then fifth one is the slice authority need to authenticate the service provider. Sixth one is a node owner provide a slice creation service for a slice authority to create slices. It essentially delegate resource management to the slice authority. A management authority delegates. Then seventh one is the management authority delegates a creation of slice to a slice authority. So this is all about the server in the distributed system. So thank you.